All right, welcome everybody to session number 4. I guess you can see a slight change to the to the front of the lecture series in casing design from the previous 3 sessions. We used to say out of 4, now it says out of 5. So this is lecture 4 out of 5 instead of 4 out of 4. Today the contract for me was signed again, so I get access to the NTNU email, my email there, and so on. But I'm not going to be able to set up the exercise for Thursday, so we're going to have a regular lecture on Thursday instead, and I'll find a time and agree with you guys via email when there will be an exercise at the computer lab. I guess most of you would be a little bit curious, at least, on how the industry software works and how you make casing design in it. So we'll run that exercise this year too, for your benefit. It doesn't really have any. It doesn't have any direct need for you guys for your exam, as per se, but only for your professional career and starting point, I guess. Any of you guys been running casing design before?
Yes, a bit.
A bit, yeah. Which software did you use? Landmark, yeah. So this is stress check Landmark that I'm trying to give you an insight in. Yeah. I'm not sure how things will be. I guess your class is about 9 people right now. Normally that could be extended a little bit with some more people in the 5th grade in the autumn. We'll never know until after school starts again, university starts up again. But if there's enough people and interest, and the room is technically up and running with the computers and so on, we could potentially set up the class where we do the simulation of making wells as they do in the industry. This class did not go last fall, but before that we had it, and yeah, not the corona years, but it has been running since 2014. Basically, there's a set of data as you would get it from the subsurface team in the industry. As a matter of fact, it is a copy of a well, and this document that you normally get would be called either recommendation to drill or statement of requirement, something like that. That's typical, and it tells you that we need for example, a gauge to measure pressure and temperature deep. It would tell you that the formation looks like this. It would have the pore pressure plot, the temperature. It would have a number of inputs standardized and agreed upon internally in each company, more or less the same package of data, all of them. And what we do in that class, we work in groups. Some they work with making well paths. Some work with drilling design. In that, we're talking about torque and drag, hydraulics, cementing, these things. And then there's a group that works with the casing design, and finally casing wear is the last group. And basically what we do is cooperate between the different groups. All drilling engineers would have a speciality. That's typical in the industry. You're not an expert on absolutely everything. Someone would specialize in cementing. Someone would specialize in drilling mud. Somebody would have other specialities. So we always talk to each other and cooperate. And that's why that class has been running like that, to cooperate. The end product of that class is actually a drilling program. And by the end of your semester, after you submit your drilling program, you will see the drilling program made by the drilling engineer back in the day that when that drilling program was made. Plus, you'll see the other classes how they solved it. That's how we've been running it. Yeah, yeah. And we do risk assessment and time planner going through the different operations. So, and we're using landmark, and we present to each other. The whole class is very different from a traditional teaching. Typically, what we do is you guys are teaching. Yeah, yeah, I'm not kidding you. You ask me any question, I guide you through the operation. It's a little bit like drinking out of a fire hose to begin with. You get the governing documentation package, you get the manuals for landmark, you get an introduction how to make it, and basically the first week or two is very busy teaching, learning situation, and you guys are discussing, and that's why it's good to work in groups and across groups. And then basically you build up your learning and you present it. Typically, the well paths are made first. That's what you need to do in the industry too. You make the well path. It's the input for absolutely all other engineering. And then the group presents what they did, how the software works, and so on in a PowerPoint to the rest of the class. And everybody else can take a note of it. They get a copy of the PowerPoint, and everybody learns all the applications, even if you're kind of in only one of them. Typically, what we've done for casing design is that the stress check is very easy. It's very straightforward. You learn that more or less enough in a day, and the other one, the Wellcat, you need a couple of weeks before you can really start to feel that this is. And there's no overview. It's just it's one of the best casing softwares in the industry. Definitely, it allows you to do so many different things. But it's like a grandmother. She wants it her way. She's so kind until you start to bullshit. Then of course everything falls apart, and you'll get it back. Yeah. That's enough about that. We have to continue here. We're at strength of pipe. We have gone through the basic material science in the first session, introduction to well construction. That was the second session, where we went through a video showing how casings are put together subsea, and we noted that it's very similar onshore, the structure. And we went on to talk about acting forces in the third session. And we're now going to go into the strength of pipe. Chapter 3, casing design process, is where we're at. And we covered already section design pressure, acting forces, as said, and now is the strength of tubulars. We talked about the acting forces contributing to each of the 4 here, or actually 3. You decompose them into triaxial at the end of the day. So we talked about all the acting forces contributing to a collapse and to a burst and to axial in the last session. Yeah, and again, this slide here is only to remind you that temperature modeling in itself is too complex for this class. All what we're going to do is have that simple equation that we talked about in the last session, and you will be given the temperature if there are any calculations to be made. I think, to be honest, there is an exercise in the exercise. There might be something about the temperature calculations. It's not as long as you know the delta T, the differential temperature is not too complicated. But if you don't, then and you have to model it, it's a different story altogether. You have to know the composition of the different fluids and their heat capacity, and you have to model for each layer first what they transmit through the steel, then the concrete, and then into the formation and so on. And it's all these three different mechanisms at the same time going through this sandwich. And as you start to go up, it's steel, maybe liquid, depending on if it's cemented fully, and then steel again, and then liquid or cement, and then formation. So it grows worse and worse as you go on top, and you have to know what you have lost in the bottom and so on. So it's yeah, you get the idea. Strength of tubulars. This curve is essential for your understanding. It tells many things. I'll see if I can do. Let me see if this is possible. We will not do that. To the left, we have pipes with the highest strength capacity. To the right, the lowest. You can see that on the vertical axis, it just says ultimate stress, and that's their stress capacity. Now on the bottom, it says D over T. That's the outer diameter divided on the wall thickness. Seems a little bit confusing, but basically pipes that fall into the category in light blue area number 1, they are very thick-walled, small diameter pipes. An example would be HPHT tubing. The production tubing would be very thick-walled and small diameter. And all the way to the right, you will have conductor type pipe, very large diameter, thick, yes, but the ratio would be very, very low. Now, what is important for you guys to take away? This is the collapse curve. The external forces that a cylindrical hollow steel structure can take. Jumping a little bit, well, a lot back in time to Euler's column theory, a solid column. In the 1700s, there was a formula that said columns, they do not really depend on the strength of the material. The yield does not come into play for the strength of it. It's only a geometrical issue, and you can see that from the formulas later. And that's all the way to the right in the green number 3. It's called elastic collapse, that segment, and it's purely mathematically derived, which means that anything that you calculate in that area is very accurate with regards to the strength of the pipe. It's no difference between well, very little difference between the theory and what we measure in reality in testing. We could say the same actually about the light blue. That is all the way at the other end of call it the curve. Very simply, it sounds a little bit out of place, but it's it's the opposite. It's probably the better to say, because it solely depends on yield. Solely depends on yield. There's no geometrical factor influencing to the degree that that we see on the other ones. It's depending on the strength, the yield, and that's very special for for a pipe. Very few pipes that we actually use in the industry at all comes into this category. In the middle, let's say it's just as simple as a mixture of the two on the side. So pipes that go very close to the blue area, they would be very much influenced by their yield strength and a little bit by the geometrical factors. And going in the area number 2, very close to area number 3, it would be a little bit influenced by yield strength and a lot by the geometry. That's as simple as it is. That's how pipes behave. If you test different DT ratio pipes, they will follow that blue curve more or less. Statistically, a little bit like on and off, up and down. Yeah. So this is the essence of collapse. And one more thing that is very important to note: you will sometimes be confused with the word buckling in this context, because that's what some people call it. Not collapse, but buckling. These pipes will buckle. That's what they say. And yeah, that's how the theory and the literature works. They say there is a buckling part in it, and to be honest, it's probably the geometry part that they are talking about. Yeah, go ahead.
Can you go over once again which type of pipes were in this
Y- yes. We see in category 3, the further to the right, it would be larger and larger diameter pipe with a thin wall. Conductors. Yeah. And all the way close or in the blue group, you would find tubing, production tubing, the smaller outer diameter pipes with very thick wall. What we normally install in our bells in the North Sea, they don't fall into the category of the blue. They will fall. They will come in this area here, I guess, close to the left of the number 2, somewhere like this. There's a curve showing this um, uh, here. Um, um, you see the DT value noted on top here in very, very small figures. I'm sorry about that. It has, let me put this one up here. Yield strength collapse. Here you see the curve. The blue one is now going in this direction, and the green one comes on top here. Okay? So these two categories are together the one in peach going in this direction. You see that they the middle group swallows 90% or more of standard pipes. Now these are the yield strength 75,000 psi. That's what they are, and it's the different DT ratios. Now you see. Let's try to find. I'll look a little bit closer. This is a 5-inch, and no, sorry, it's a pound per foot on top. So it's a 5-inch, 24.1 pound per foot. Quite thick walled. Yeah, and a standard 7-inch. Well, this one is 38 pound per foot. That's not very standard. Let us find. This one we used in the Åsgard field, 35 pound per foot. But normally the 7-inch is 29 pound per foot, which is, yeah, here. You see it here. It goes into this part. Let's say this is the central group number 2, so it falls in this category. Yeah. So that's the standard production tubing in the Norwegian sector. You'll also find a lot of this type. Yeah. Yield strength would be slightly higher, which means um, uh, this this limit would go slightly down for P110, but that's not the normal production tubing. Normally, we go around L80 for production tubing, for example, and casing for that matter could be, well, that one is 110. So for that one, it will go a little bit down. Yeah, we see a curve here. This that tells you a little bit how the different categories of collapse varies with the yield strength for the DT ratio. Yeah. This graph is a little bit confusing, at least now that you guys have seen this for the first time. Yeah, it just gives you a reflection. I have to make a step back and tell you why the peach has been number two has been split into two. That has the historical significance from a work that was done in early 1960s. What the industry experienced was a lot of collapse of pipes, and they wanted to know how can we make good calculations for pipes so that we know how to design our wells properly and avoid collapse. And what they did, they collapsed some 2,300-400 pipes in was it N80 and another yield strength, and there were two sizes. They collapsed as far as I remember, and they made like a graph showing in the DT ratio where are we going, and they extrapolated these results, so they are valid for all pipes, and they made this into what they call the API collapse calculations. They are the ones that the industry is using today as a standard. But if you look into the standards, you'll find these calculations as the primary, and they are the primary calculations in the casing design software that you guys will meet. Yeah, curve fitting, mathematically curve fitting, that's what they are. You saw just now that most pipes fall into the peach category, right? And there's no one formula that covers mathematically the curve fitting that goes on to mathematically represent the behavior, collapse behavior of pipe. So what they did, they had to split the area number two into two categories, and they call it plastic and transition collapse. And there are two different mathematical formulas for those, and they are only based upon this work from the 1960s. That's the story behind the plastic and transition collapse. They are not really two groups. It's basically one. It's just made like this from the API collapse calculations. Yeah. Yeah. Go ahead.
When you say collapse, is it mostly collapse from outside and collapsing inwards, or more like the buckling type of collapse that you're thinking about?
Yeah. Let me explain. Thank you for the question. Very good question. Let's have a look at this. Let's see if we can explain that in a better way. If you have a DT ratio here, it will be a purely buckling type collapse. You will have some force on the pipe that is dominated externally of the pipe, right? That's basically a collapse force. There might be something on the inside, but it's much bigger on the outside of the pipe, right? And then we say that the pipe buckles. We don't say that it collapses, we say it buckles. And then if we go in this area here, I don't know if you can see my cursor. Yes, you can. It would still have a buckling type failure. Still, we call them collapse calculations. We also call this collapse calculation the elastic collapse is still yeah, but it has both names, right? Um, I'm not sure that you would say that category one here, the yield strength collapse, actually buckles. Technically, buckling, as I see it, is a geometrical, tied into a geometrical feature, which is true starting from this uh, category, number two, and all the way here. So I wouldn't say buckling for the yields, those pipes with a DT ratio that falls in the yield strength. All other ones has a buckling component for collapse, and this one would have a pure buckling, would be equal to collapse, if you say what I mean, in category three, right? Yeah. So yeah, and once a pipe has some buckling, then the collapse is yeah. If you have some deformity of a pipe, then it collapses easier, right? Yeah.
Can I ask a question, please?
Yeah, yeah. Go ahead.
So if you, I mean, you, maybe our pipe is facing external pressure and it collapse, and based on DT, we can say that we are maybe in the collapse number one,
Yep.
collapse number two, or collapse number three, depending on.
Yeah, yeah. These collapse calculations, and we'll see that shortly how they are and how you determine exactly what you're saying. The DT ratio to determine your grouping is it's very simple. That's a easy mathematical thing. Up until the point you have casing wear, of course. then, then like okay, it changes. Yeah. This is how it looks. A collapsed pipe. Typically, external forces have been the dominant ones. Now, yeah, there are so many things we could talk about here. A partial support of cement, for example, has a large effect on cement. No, sorry, on collapse capacity. Yeah. So and these things are not incorporated in this class, or for that matter, in casing design normally. Why? Because you can't rely on it. You have access to some logs and you can have an idea, and there are tests in papers and so on, so that you have an understanding, if you have logs and everything else, that am I better off than what my casing design calculations show me, or are they real? Worst case, that's what we go for in casing design. Worst case, it means that we always calculate that there is no support other than the formation natural pore pressure. Yeah, go ahead.
Does sinusoidal ducting, for instance, also follow the curve for drill pipe when you have just that to be a different kind of ducting, like not inwards, but you have
S type. Yeah, yeah. Okay, I will answer this question because this is very important, I think, for you guys as drilling engineers. Basically, I do not take sinusoidal buckling as serious as helical buckling for drill pipe. Why? My first thing to do, my checkpoint to see if I worry or not, is basically this. If we have a 13.38 and then a 9.58-inch liner, and then you're drilling 8.5 inch, for example. or bit. Then I'm worried. If the 958 goes with a tie back like this, I am no longer worried. Simply because the drill pipe will have couplings that give you very little tolerance here. There is no room to buckle. Basically, what happens? You just stop, right? And then you know that, okay, I've gone too far with my weight. Whereas if you have a situation like this, then the pipe has so much room to move that buckling becomes very, very dangerous. You can actually break the pipe, and you can physically do a lot of damage, both with regards to casing wear and to the physical properties of the pipe whatsoever. You can do a whole lot of damage. But whereas when it's so tight as here, it just stops, doesn't it? Of course, you don't want any buckling, and if you see that your extreme case gives you sinusoidal buckling, you have still a lot of room up until that point, right? And if you touch sinusoidal, fine. In a case like this, I don't worry too much. That's fine. I don't plan on taking it and then touch upon helical buckling. That's too much, right? Helical buckling in this case also is bad. Is bad. It gives you extreme friction and extreme casing wear. So don't do that. Yeah, go ahead. Yeah, sinusoidal. Then you have like an S shape going like this, like a snake. Whereas helical buckling, that is a corkscrew. You have uh, twisted your pipe or bent it or you have applied so much physical to it that it has become into a screw shape, corkscrew shape. Yeah, yeah, burst. Of course, back to the first session with material science. That's our understanding of what it is. I'll put back to you the curve up in the right corner. You remember we did that tensile testing of that specimen that is just like a rod, right? And again, the yield point, definition of yield for steel is when you make a permanent 0.2% deformation. You stretch it further, you deform it more, right? But that's the yield point, 0.2% permanent deformation. If you go a little bit further down, you'll find the elastic point, where the linear you pull it up to this point, the elastic end point there, and it goes back into the same perfect shape every single time, right? And this is yield. We call it yield, 0.2% deformation. And that's the design limit for internal forces, pure internal forces. The industry uses the Barlow formula, which was made in 1836. You're not blinking, but I blink always when I see this one. Why? Because it was made before we had proper science in this area, long before. So this was a very good, Barlow was a very good mathematician. Only what it says and why it's not recommended as a design formula in ISO and API is that it makes a few assumptions that are not entirely correct. And it's like a coincidence that actually it has it works for most pipe. It does, and it has been used forever in the industry. And basically, like I said in the first session, the industry doesn't change anything that works. It's like an old Volkswagen Beetle. It takes you every day, cold or warm weather, it takes you there. It doesn't fail you. So then, and that's the same with this formula. It doesn't really fail too much. One thing that makes me double blink is, of course, this factor of 12.5 or 0.875. 87.5% is what it is, or the wall thickness. And that's a really old design factor. I think I mentioned it before. It's basically a manufacturing standard saying that pipe should never be manufactured with less than 12.5% wall loss, if you see what I mean. If it has supposed to have 1 inch thick wall, then it can't be at any point smaller than 0.875 inches. Okay, that's what it means. Now, the truth of it is, if you look into the standard and you work the math a little bit there, you see that the industry doesn't produce pipe that is smaller than 0.95. That's they have tens of thousands of measurements on random pipes, and that's how it is. And they still keep this old standard. Imagine that. So when you calculate burst, there's a lot of hidden safety factor, just as in the collapse. We'll see that when we get to modern collapse calculations later on. Yeah. When you look at burst and you're saying that's my design limit, it's actually much more difficult than collapse. Collapse, you see it immediately, right? Oh, that's too much. Right? Oops. So that's very clear. It collapse fails at the design limit. Burst doesn't fail at the design limit. It starts to yield, permanently yield, right? And we never see that really, do we? In our wells, that we have permanently yielded our pipes. That's not physically very possible. Now, the drawings that we see here is called rupture. And we say that in your kitchen, for example, or ever if you go by on the road and you see some excavator going there, and the water is just, you say that the pipe has burst, right? So don't make the mistake of thinking that these are burst or as per se. When we talk about burst, it's only to the yield point. Yeah. Whereas what the drawings here show is rupture, and rupture is at the end of the red curve of the yield here. Here, it's here. That's when you rupture the pipe. Then it has gone through all the physical deformation it can take, and it gives up. The metal bond is broken into a rupture. This is how a axial compression combined with burst looks like. You have an internal pressure dominance and you have compressive forces, then you will have a pipe like this. Now, just for your case, we're out of time, but I will add this very quickly. Think about a well, any well. Let's see if I have a drawing of a well here. Yeah, here. This well, if you see it doesn't have compression more or less anywhere, does it? Everything is vertical. All casings would have zero axial pressure at the bottom, right? It's hanging from the casing hanger. When you start to have deviated wells, you will have some compression in your bottom. You may have some compression from, say, cementation, that the density is much higher on the outside, but it's not really significant. is when you have those long horizontals, when you come to having the full section in the horizontal going into some serious compression. So this that should tell you something about when you get wrinkling. Rarely, right? It doesn't happen very often. All right, I guess you guys are ready for your first break.